we dwell on Ernest Rutherford's remarkable series of discoveries, let us get to know the scientist better and go back in time. The British physicist was the son of James and Martha Rutherford. He grew up in a poor but hard-working family. He had a typical childhood, which included milking cows, fetching firewood, and feeding the chickens and pigs. Ernest and his sibling also spent their time bird nesting, fishing, swimming, and making bows and arrows. It was at Brightwater School that Ernest was introduced to science. His teacher there gave him his first science book. Since then, Ernest Rutherford has been fascinated by science, its magic, and its wonders. However, to continue his education, he needed to win a scholarship at Nelson College. The only catch is that one student out of 50 would be accepted. Ernest did fail his first attempt, but like what his teacher said, he didn't lose hope. He worked harder than before and with perseverance, he finally able to knock down that scholarship. Later, he entered Nelson College. He also won a further scholarship to attend university. Years later, after graduating and attending other universities, he left New Zealand to study at Cavendish Laboratory, Cambridge as a research student. One day, the discovery of radioactivity in uranium salts by a French scientist named Antoine Henry Becquerel was all over the news. Having just completed his research concerning X-rays, Ernest Rutherford decided to study the rays given off by uranium and conducted an experiment. So, Rutherford began to work with uranium rays, thinking that uranium rays are very similar to X-rays.
Please set up the following materials and equipment. We will conduct an experiment.
Is this about the latest news, sir, concerning radioactivity?
Why yes, this seems like a natural evolution to my study about X-rays. X-rays and the remarkable properties created the most intense interest throughout the scientific world. It occurred to several physicists to try whether ordinary bodies emitted a similar radiation, which was able to pass through matter opaque to ordinary light.
But why use an electrometer, sir? Didn't Becquerel use the technique of photographic plates? Why not use the same?
You see, Henry Becquerel concluded that the uranium radiation consisted of rays which were unequally absorbed. That is to say, that the uranium radiation was made of two or more distinct parts. But with his crude photographic plate technique, he could go no farther. Besides, a quantitative determination of radioactivity is necessary.
I see. So at the same time, we are also here to check whether what he said was true or not.
Correct. Shall we start then?
Okay, the apparatus are all ready. What do you want me to do?
Thus, Rutherford and his co-workers proceeded with the process by thin sheets of metal foil. He then covered the uranium with aluminum sheets of various thickness and measured the current using the electrometer. Finally, they come to an end with positive results.
So this leaves us to conclude that there are two parts to the uranium rays. One is easily absorbed,
and the other one passed through 100 times as much foil before it was absorbed.
How about we name the easily absorbed one alpha and the more penetrating beta?
That could be. The alpha rays are very readily absorbed by a thin metal foil and by a few centimeters of air. They have been shown to consist of a positively charged atoms projected with a velocity of about 1/15 the velocity of light. They are deflected by intense and magnetic and electric fields.
The beta rays are on the average far more penetrating. They are far more readily deflected than the alpha rays.
Shortly thereafter, a third form of radiation, named gamma, was discovered that can penetrate as much as several centimeters of lead. It was also concluded that A rays and B rays were actually streams of particles, while Y rays are in charge. After this discovery of alpha and beta particles, later in the year of 1906, Rutherford suspected that the alpha particles were actually helium atoms stripped of their electrons. This led him to demand a high standard of proof and conduct another experiment.
William, I am going to need your help this time.
Sure. Is this the one you've been suspecting? that the alpha particles are from helium atoms?
Yes, however, we need a high standard proof for this one. Actually, I was thinking about using big electromagnets with big voltages to divert alpha particles.
Don't you think that will be a little too costly? I mean, we have to spend $1 million.
Well, you sure were not mistaken on that one. Without the strong electric and magnetic fields, however, we won't be able to measure more directly the charge and mass of the alpha particles. But then, I guess we should think of a new line of attack.
Hmm. Hey, why not just go for the usual? I mean, a chemical procedure mixed with physics. What do you think?
Aha! William, collect alpha particles and seal them in a glass tube. Compress them and pass an electric spark through.
Let me guess. We are going to study the emitted light in a spectroscope. Am I right?
Correct. Let's get ready.
And so they did. They studied the emitted light and found it to be identical, the spectrum of helium, within a few months. Ernest Rutherford was awarded the Nobel Prize for Chemistry.
Your Highness, ladies and gentlemen, the lucky winner of the Nobel Prize of Chemistry of this year 1908 will be introduced by representatives of the Royal Academies of Science. A round of applause. Nobel Prize for Chemistry goes to Mr. Ernest Rutherford for his investigation about the integration of the elements and the chemical of chemistry.
Gold foil experiment, the atoms were thought to be a blob with positive and negative charges. But before Ernest Rutherford could study the effects of the particles on matter, he had to develop a way of counting individual particles. With the help of his assistant, Hans Jigger, he bombarded a piece of gold foil with alpha particles emitted by a radioactive material.
Sir, here's the radioactive source, radium, which I kept in a thick red block with a small opening.
Good. Now direct it head-on into the thin gold foil. It will direct a beam of alpha, which is heavy with positively charged particles.
The small opening will surely let out a beam of light and will pass through the gold foil. This fluorescent screen here will emit a flash of light when hit by an alpha particle.
We should also use a detector to count the number of alpha particles at each angle of deflection.
Of course, let's see what will happen then.
The experiment they conducted was very laborious, for they sat and waited for hours in a dark room, holding a tiny fluorescent screen and looking just by eye for flashes of light. Also, as Rutherford deduced, most of the gold foil is empty space, so the alpha particles go straight through, doesn't hit anything and goes through in a straight line. Or so he thought.
Did you see that? A narrow beam of particles broadened when it passed through a thin film of metal. Did you get the measure of the angle through which these particles were scattered?
Yes, this scattering was small though, in the order of 1 degree. I also noted that although most of the particles passed right through the gold foil, a very small percentage, about 1 in 8,000, would bounce back.
Good gracious, I thought they would pass through the metal foil the way a bullet would penetrate sand. There must be something hard inside that caused a few of the alpha particles to ricochet.
This must mean that the raisin bread model was wrong.
Indeed, it seems that the mass and positive charges cannot be evenly distributed in the atom. There was a small dense portion of matter that deflected the particles. This must mean that the mass of the atom is concentrated in a small positively charged area. Seriously, it was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you.
Ernest explains these results through equations that predicted that the number of alpha particles scattered through a given angle should be proportional to the thickness of the foil and the square of the charge on the nucleus. and inversely proportional to the velocity with which the particles move raised to the fourth power. When he published the result of these experiments in 1911, his discoveries led to our current understanding of the structure of the atom. Finally, in 1919, it was in the Cavendish laboratory that he made his final major achievement, the artificial alteration of nuclear and atomic structure. By bombarding nitrogen and alpha particles, Rutherford demonstrated the production of a different element, oxygen,